Has the enigma of the Hubble tension finally been unraveled? One of the biggest puzzles in astrophysics is the fact that the universe is expanding faster than theoretical predictions suggest. However, researchers from the universities of Bonn and St may have found a key to solving this persistent mystery. Their findings suggest that the Milky Way could be situated in an enormous cosmic void, an exceptionally empty region of space. Intriguingly, when an alternative theory of gravity is applied, the gap between the predicted and observed expansion rates of the universe appears to resolve itself. Yet there's a significant caveat to this groundbreaking idea. It directly challenges the foundations of the standard cosmological model. What has long been part of the basics of astronomy today marked no less than a profound paradigm shift about 100 years ago. For generations, researchers of the past were convinced that the cosmos was a rigid, unchanging construct. Even a certain Albert Einstein initially held on to the idea of a static universe to such an extent that he added a cosmological constant to his equations, a step he later regretted as the greatest folly of his life. And although the young Belgian priest and astrophysicist Georges Lemaitre had already shown Einstein in 1927 how a mathematical model describing an expanding universe could be developed from the general theory of relativity, Einstein dismissed this concept as a mere mathematical gimmick. In retrospect, however, we know that Lemaitre's findings had a decisive advantage. After all, they made a prediction that could actually be observed. Specifically, it bridged the gap between the expansion of the universe and the light from galaxies. If the universe is truly expanding, then other galaxies should be moving away from us, just like dots on a balloon spread apart as it inflates. Similarly, as light from these galaxies travels toward us, its wavelengths would stretch, shifting the light toward the red end of the spectrum. In the late 1920s, American astronomer Edwin Hubble confirmed this phenomenon. Through meticulous observations of numerous galaxies at the Mount Wilson Observatory in California, he found that their light was indeed redshifted, providing concrete evidence of the universe's expansion. This discovery also led to a profound realization. If the universe is continuously expanding, then tracing this process backward suggests it must have originated from a single, incredibly dense point. This idea now forms the foundation of the Big Bang theory. By the 1990s, astronomers uncovered yet another surprising fact. Not only is the universe expanding, but the rate of expansion is accelerating. Scientists attribute this acceleration to dark energy, an enigmatic force believed to counteract gravity and drive the cosmos apart at an ever-increasing pace. The mysterious Hubble tension raises a fundamental question about the universe's expansion. Why is it happening faster than expected? At the core of this cosmic puzzle lies the challenge of determining the exact expansion rate. On paper, this rate is represented by the Hubble constant, but in practice, its precise measurement has led to conflicting results, collectively known as the Hubble tension. According to the standard model, the Hubble constant should be around 67 kilometers per second per megaparsec. To put this into perspective, 1 megaparsec, MEP, is about 3.26 million light-years, while 1 light-year is 9.46 trillion kilometers. This means that the speed at which galaxies move away from each other increases by 67 kilometers per second every 3.26 million light-years, translating to an impressive 244,000 kilometers per hour per megaparsec. However, it can be significantly faster. These theoretical predictions contrast with direct astronomical measurements using supernovae, gravitational lenses, variable stars, or red giants, which yield a Hubble constant of 73 kilometers per second per megaparsec, equivalent to 264,000 kilometers per hour per megaparsec, resulting in a discrepancy of 20,000 kilometers per hour per megaparsec. How can this significantly higher value be explained? Could previous studies have been affected by measurement errors? This question was addressed by the James Webb Space Telescope when it re-examined data from the Hubble Space Telescope. A research team, led by Nobel Prize-winning physicist Adam Rees from Johns Hopkins University in Baltimore, analyzed Webb's data from the past 2 years. Given Webb's vastly superior capabilities compared to its predecessors, experts describe it as providing a high-definition view of the universe. As a result, Webb's data offered a precise confirmation of the Hubble tension. The most comprehensive Webb dataset to date, including supernovae, variable stars, red giants, and carbon-rich giant stars, affirmed that the universe is not behaving as expected. The latest analysis determined a Hubble constant of 72.6 kilometers per second per megaparsec. According to Rees, the gap between the predicted and observed expansion rates indicates that our understanding of the universe remains incomplete. One possibility is that an overlooked factor provided an unexpected boost to the early universe after the Big Bang. Alternatively, dark energy may be evolving. Perhaps it is denser or more intense today than in previous cosmic eras. However, scientists are also considering alternative explanations beyond dark energy. One intriguing hypothesis suggests that the Milky Way, including Earth, could be situated within an enormous cosmic structure known as a supervoid. To understand what this gigantic void is all about, we first have to recall the overarching structure of the universe. As is well known, stars and planetary systems are found in galaxies, which in turn combine to form galaxy clusters and then form superclusters. For a long time, researchers saw the largest coherent structures in the universe in such superclusters. But then large-scale surveys showed that the superclusters are by no means randomly distributed in space, but rather arranged in a network-like structure. The lattice of this structure is formed by long fibers known as filaments, which can be several hundred million light-years across. In the same breath, the filaments also span gigantic, virtually matter-free bubbles, the so-called voids. And although the nightly view of the firmament resembles an exuberant astronomical spectacle, some researchers assume that these cavities even make up the majority of the cosmos. Expressed in figures, this means that an estimated 50 to 90% of the universe is characterized by a yawning void of matter. A study led by Sergei Marrow from the University of Bonn suggests that cosmic voids might directly contribute to solving the mystery of the universe's expansion. Conducted in collaboration with researchers from the University of St Andrews in Scotland, the study is based on new observations indicating that Earth resides in a region of space with relatively low matter density, similar to an air bubble in a cake. As a result, the surrounding matter is denser, generating gravitational forces that pull galaxies within the void toward its edges. This seemingly straightforward concept implies that galaxies are receding from us faster than expected. In this context, variations in the Hubble constant can be attributed to this local underdensity, a simple yet significant explanation. However, there is a fundamental issue. The standard cosmological model does not account for such voids, as it assumes a uniform distribution of matter and space. But how then can the 600 million light-year distant galaxies be explained, for example, which were examined by another research group and which are moving away from us 4 times faster than the standard model of cosmology allows? Well, in this regard, Pavel Kupa, who is also involved in the void study, states that the standard model is based on a theory of the nature of gravity proposed by Einstein, and that gravitational forces may behave differently than the creator of the theory of relativity expected. Specifically, the research groups at the universities of Bonn and St Andrews used a modified theory of gravity in their computer simulation. The modified Newtonian dynamics, or MON for short, was proposed by the Israeli physicist Moti Milgram around 40 years ago and is still considered an outsider theory today. And yet, MON predicts the existence of huge empty bubbles in space, and that is precisely the crucial point. Because if gravity actually behaves as Milgram assumes, the problem of the Hubble tension would disappear in one fell swoop. Since the observed deviations stem from irregularities in the distribution of matter, there would be only one constant governing the expansion of the universe. However, This would also require abandoning the well-established theories of Newton and Einstein regarding the nature of gravity. Kupa argues that this presents a major obstacle to research. Specifically, the astrophysicist highlights the strong influence of established theories, which play a decisive role in the allocation of research funding. Alternative approaches that challenge long-accepted ideas are often dismissed as unscientific, making it even harder to secure financial support from relevant committees. By the way, our committee has just approved your free subscription. Glad to have you on board.